Hello. I want to discuss a topic, uh, polar coordinate integration, and maybe a little bit of spherical coordinate integration, and to explain what's really going on behind the scenes, so to speak. So let's get started. Let's get rid of this first. All right, here we go. So what's really going on when we do this? Now, what we told you in class is that if you have, let's discuss polar first. And what we really told you in class is that if you have a two variable function over, and you want to integrate it over an area, and here, remember the dA is either dy dx or dx dy as it may be, and you want to switch to polar coordinates, what you do is you get the following integral. This is I'm going to call this a transformed region. This is f of r cosine theta, r sine theta. And then we have the r dr d theta. And we had this r as a type of stretch factor. And where this came about, we were told, is that if you're looking at the xy plane, the standard Cartesian plane, and let's say we just took these are lines of constant theta. And here, this is a dr, and this is a d theta. Then if we took, well, this is not a great drawing. If we took a comparable dr, if we took the same dr and the same d theta, there's a lot more area here. And that's where that factor of r comes from, because it's really r times as big for the same dr d theta. And we talked about, chopping this up into little things. And sometimes in class, I refer to this dr d theta as the area element. So let's just do a kind of a sample problem to sort of set this up. So suppose, for example, we wanted to find the area of a circle, or inside a circle. Of radius r. And in the rectangular domain, we had something like this. So this was an r right here. So in the rectangular coordinates, we're integrating the function 1. And if we wanted to do dy, well, let's say, since this was a case here, this led to r squared minus x squared is y squared. So if we sliced in this direction using the rectangular coordinates, y was equal to minus the square root of r squared minus x squared. This is equal to r squared minus x squared. And then the x, goes from minus r to r. And this was dy dx. And we were told that you have to transform this into this integral here. This was your r dr d theta. Your r went from 0 to big R, and your theta goes all the way around. And in the polar system, instead of taking these little dx dy blocks, we had these little things that look like this, where this was a dr and d theta, and we added those up. And you say, so when you took this integral here, that was no big deal. I chose an easy one on purpose. And what we end up getting, evaluating big R squared over 2 minus 0. You're going to integrate this from 0 to 2 pi. And you get the famous pi R squared, as expected. Okay, that was a calculation, and we told you, like in this xy plane, you just divot these up into these small, the dx's dy's were now these, where these were sort of warped little rectangle-like things. But what's really going on? Well, let's look at this integral here, this whole integral right here. This integral, you can see, is the integral of r over a rectangle in our theta space. So let's just draw a coordinate system like this, where this was a r and this axis is a theta. And let's see what's going on here. And we know this circle right here, x squared plus y squared equals big R squared. Well, that's transformed into, well, I'm going to let this theta here, I'm going to let this theta here be a 0. And let's go up to theta equals 2 pi. And that goes all the way around. And this R, this blue R, is going to be R equals capital R. So what do you notice? This whole circle under this transformation is taken to this line segment. So this blue thing right here, it starts with theta equals 0, goes to theta equals pi over 2, to theta equals pi, and so forth. 3 pi over 2, right here, finally to 2 pi. You see that? So this circle here, this blue circle is changed to this line here. And a constant theta, and this is what's kind of interesting. Let's just look at a theta constant. Let's say this is theta equals pi over 4. Well, this red line is transformed into this red line here. So these lines of constant theta that start at the origin are transformed into these. Now, what the heck is going on here? Well, let's try to visualize this. This point right here, in fact, let's just circle it in maroon here. This maroon thing, let's call that R equals 0. Well, all equals 0 is this entire line. So what we see is that this entire line, this whole line, R equals 0, is squished under this transformation to this one point, right? Now that's very interesting here. So, and what's happening is that since these lines are constant theta, let's do a theta equal, let's say pi over 2 right here. Well, that goes to this. Well, notice they all have their origins right on this R equals 0. And so what we're doing is when you squish this, there's two things are happening. All these constant theta rays, well, their endpoints are staying on this. And remember, this whole thing, imagine squeezing this R equals 0, I guess, segment or the entire line into one point. These things go to one point, and then these rays, when you squish them together, they become rays from the origin, and there's a second identification. This, I'll do this in green. This theta equals 2 pi right here gets identified with this. So imagine taking this. So the identification, think about this little square, and I'll try to do it in stages. So you take this little square right here. This is 2 pi for theta. This is 0 for theta. This is going to be your r equals 0. And let's say the blue will be r equal big R. What you're doing is you're imagining or squishing this whole thing here to make these things come together. And let's put in a couple of other little rays here, theta rays, like so. So if you squish this together and you take this and stretch that and put it on itself, if we have viewed this as a process, this purple, you can now think of this. You can think of your green right here, and this green being right here. And this blue is starting to be stretched around like this. So you've taken this and you've stretched it to where it's perpendicular. You've squished this a little bit. Then if you complete the process by taking this green and putting it right on top of this other green, this now has become one line. The blue has gone all the way around, so to speak. And the R has been demolished into one point. So this whole thing here has been squeezed. These two things now lie on top of each other. And this is a little bit bad here. Oh, it's a lot bad actually. That blue should come on top of each other. So imagine the action of doing that. Whoops, I meant for that to be blue, this color blue right here. That's what's going on. Okay. This thing just goes and collapses on itself, and you have this little wedge right here. So notice there's a singularity at r equals 0. And the other thing to think about is in doing this, this little, I'm going to put this in orange here, this little pi thing, in this space, when you take it out, that becomes a rectangle, but the area for the same dr, d theta, it matters whether it's up here or down here. So the area there is distorted. So when you're doing the transformation, what you're really doing is you're taking a function in this space, you're changing the coordinates to be in r theta land, and you really are distorting the function you're integrating. C1 becomes an r here. So when you actually do the integral right here, notice we integrated that as if this were x's and y's. And that's because you're actually doing the integration in this space right here. But in order for you to get the same answer, you have to account for the distortion between the two. So that's what's really going on when you do a polar integral. Now you can say more about that in advanced calculus courses. This is discussed in greater detail. Now, I should mention something about where the R is actually calculated from. You'll learn in advanced courses, it's going to be the absolute value of the determinant of the Jacobian transformation matrix. And you'll learn about that later. It has to be absolute value. And since x is r cosine theta, it's cosine theta minus r sine theta, sine theta, or cosine theta. And you're going to take the absolute value of this determinant. So you cross multiply. And that works out to be absolute r, which is r. All right. And notice, now if you had a little bit of linear algebra, notice the determinant of the Jacobian is 0 at r equals 0. That's for the matrix is singular. You probably learned that in linear algebra. And you can see the reason for the singularity is this entire segment, or if you want to look at the whole r theta plane, entire line, is squished down to a single point. That's a very definition. Well, that's a classic singularity, I should say. It's not the only kind you can have. But several points in this space get identified as only one here. Then you do have this thing being clamped on top of that. Now let's say a couple words about spherical. Now in spherical, it's going to be a little bit harder to talk about just because of the dimensions. But in spherical, you know that rho equals a constant. Let's say rho equals 1. That corresponds to a sphere in x, y, z land. Well, in the rho theta phi space, that corresponds to a plane. So in this transformation, we take an entire plane and somehow turn it into a circle. Now, how is that going to happen? Well, notice here, one big singularity is if we take rho equals 0, that should be this plane right here, right? Well, this entire plane gets mapped to a single point, right? To a single point right here. So that's one thing. Now, let's look at theta being constant. Well, theta is going to be measured this way. Well, that's going to be theta equal constant, and that's going to map to a plane like so. So this plane here, and we're going to only start to the origin, gets mapped to something like this, right? So that is sort of a plane-to-plane map. The most interesting map, though, is we take phi equal a constant. So let's phi be non-zero and not pi over 2. Well, that's going to be phi equals constant, where phi is measured from here to there. Well, that's going to be a constant up here. That's going to be a plane. So this cone part right here gets mapped to a plane. And the reason that works is that this rho equals 0 is all along this plane here. Remember, this entire plane gets squished to a point. So that's sort of, when you take this, you can imagine taking the cone for phi equals constant and making it much wider still, until this cone point is in the center, and it's like a large giant plane, if you will. So you're really taking this cone and sort of smashing it, driving this point here, the rho equals 0 point, into here. But remember, in this space, rho equals 0 is an entire plane. So that's what's going on with those. Now, we also know that the volume element here is rho squared sine phi. And you were probably told that it's going to be the absolute value of the determinant of this matrix, partial x, partial rho, partial x, partial theta, partial x, partial phi. And I'll just write this all down. I'm not going to do the entire determinant because it takes a little time. And that turns out to be the absolute value of the determinant of, well, that's going to be sine phi cosine theta minus rho sine phi sine theta and rho cosine phi cosine theta. For y, it's going to be sine phi sine theta, rho sine phi cosine theta, and rho cosine phi cosine theta. I mean sine theta. My bad. And then for the z, it's just going to be cosine phi. There's no theta with z. And then this one here, the derivative of cosine is minus sine. So you end up taking the absolute value of this determinant, and it turns out to be this, and it takes a little bit of time to see. So let's look at where's the singular. Well, this will be singular at rho equals 0 and phi equals 0 and pi. Now let's see what happens there. Well, this one we already understood. We already understood that in rho theta phi space, this rho equals 0, which is this whole plane, gets squished down to a single point. So that's somewhat easy to understand. Now, if we take phi equals 0, that's this whole xy plane right here. Well, if we take a look in our spherical coordinates as viewed in space, the phi equals 0, let's just do this, is simply this ray right here. It's not a cone, but rather a ray, right? And that goes to an entire plane. So this plane goes to this plane, gets squashed down to a segment. So it loses one dimension. Now notice, in the case of rho equals 0, an entire two-dimensional thing gets squashed down to a point. So it loses 2 dimensions. And notice that's a square. That's not a coincidence. Okay? Lose 2 dimensions there. Here you lose 1 dimension. And then you get down to pi. Let's say phi equals pi down here. That makes this singular. And notice phi equals pi is a plane, let's say something like this. And this whole plane gets squashed down to a ray. So you lose 1 dimension. You lose 2 dimensions, though, because rho equals 0 is 2-dimensional and it gets squashed down to a single point. So that is a little bit about what's going on with these coordinates. If you want a more detailed, accurate description taking a course in advanced calculus. So thanks for watching.